Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello, dear students. Welcome back to this TV Learning Series program. I'm teacher Patrick, and today I'll be revising with Senior 3. And you remember last time we were on the Unit 3. Sorry, I beg your pardon. We're on the Unit 5, which is the rate of reactions. And we have come to the end of this unit. And as we come to the end of this unit, we always do the assessment to evaluate ourselves of how much we have retained along the unit. So our objective today, because we'll have a number of questions to answer, so we'll be expected to give the correct answers only. So if we're able to give the correct answers, then that means we have achieved our objective, and that means we have understood the lesson, the unit, very well. So before we look at these questions, I just wanted to take you through probably make a summary of what we had looked at in this unit. Remember, in the first unit, we had to define in the first lesson, we had to define the rate of reaction. In defining the rate of reaction, if you remember very well, we said this is the measure of how fast the reaction can go. The measure of how fast the reaction can go. That means if the reactants of given concentration are reacting together, so a certain amount of reactants to be converted, how long will it take a certain reactant to be converted into the product, depending on the type of the reactant or depending on the type of the reaction. The measure of how long, this is the measure of how fast the reaction can go. So that is briefly how we can, but we can even have as many definitions as possible, depending on the reaction that is taking place. Now, you remember, after looking at that, we looked at how we can measure the rate of the reaction. So we looked at the measurement of rates of reactions. If you remember very well, we looked at different ways, different methods, whereby we used specific reactions to measure the rates of the reaction. For example, if you remember very well, this is the example that we used. High zinc combining with HCl to form the zinc chloride, which is a solution plus the hydrogen gas. And we said for this reaction, we can determine how much of the oxygen, how much of the hydrogen is produced by measuring some constant intervals of time. How much of the volume of hydrogen is produced in specific time, specific constant intervals of time. Or we said we can measure how much in terms of the mass of zinc that will be reduced as time goes on. So how much of the reactant, how much of the zinc metal is used up during as the reaction goes along. Or we can use any other reaction. If we use calcium carbonate plus hydrochloric acid, this will also give calcium chloride plus carbon dioxide plus water. It still gives the gas, carbon dioxide. So how much of the carbon dioxide is produced? Or how much of the calcium carbonate is being used up. And we interpreted these reactions using different graphs, if you remember. And then we looked at, if you remember very well, the experiment that we did about the effect of the concentration. How, if you remember that reaction whereby we had the sodium thiosulfate reacting with the hydrochloric acid and giving sodium chloride plus sulfur dioxide plus the water. If you remember this reaction, we said this sulfur dioxide, or rather sulfur metal, is produced. Sodium thiosulfate and hydrochloric acid react together to produce a precipitate. So we are determining after how long this sulfur precipitate, this was formed as a yellow cloudy precipitate. And we are determining how long will it take for this precipitate to form. So when we are determining how long, then that means we are determining the rate of the reaction at which the sulfur or that yellow cloudy precipitate is formed. So we used the change of color of the sulfur that is being formed to determine how fast this reaction goes along with respect to the concentration of sodium thiosulfate. So we looked in the second lesson, we were able to look at the factors. Actually, that was the third lesson. We were able to look at the factors that influence the rate of reactions. And we mentioned a number of factors. If you remember very well, we had looked at the concentration in lesson 2. We had to look at the effect of the temperature, and we looked at the effect of pressure. We looked at the effect of the catalyst. And then we were supposed to look at the effect of light as well. Probably I had given even the homework for you to find the effect of light on this reaction. Concentration, briefly, we said when the concentration of the reactants are high, we'll have more collisions. We talked about the collision theory. More collisions, more particles, chances of the particles coming together. For example, I can just have, assuming these are particles together, the reacting particles, and then you compare them with this. So this is a certain solution, and this is another solution A, and this is another solution. These are particles within the solution. So here, there are more particles. If you remember very well, I said reactions take place by chance. Particles colliding with each other, particles hitting each other. So here, there are more chances that these particles, because they are in random motion, that these particles are likely to meet and collide. So as they collide, the reaction takes place. Here, there are few particles in B. So that means the fewer the particles, then the less the number of the less the frequency of the collisions that may take place. So that means we expect the reaction here to be slow, to be lower, because the number of collisions that will take place here will be few. So that is the effective collisions will lower. There are more effective collisions within A because of increase in the number of particles that are combining, hitting one another. When we talked about the temperature, this makes sense as well. When we look at the temperature, I said when assuming this substance, you apply heat to this substance A, When you apply the heat, you remember molecules are in constant motion. So the molecules will collide with one another more faster. So when they move fast, then that means more collisions and effective collisions, more frequency. The reaction will take place faster. With pressure, we said that affects only, this affects only gaseous molecules. Gaseous molecules. Because we said solids are incompressible, liquids are incompressible, so that is why the pressure also only affects the molecules with gaseous, molecules which are in gaseous form. The same applies because it makes sense when the gaseous molecules are squeezed together in a small volume. What happens? That means small volume means what? More particles coming close together. And as a result of that, effective collisions taking place, the reaction will be faster. Catalyst, we mentioned that the catalyst provides another route that lowers the activation energy. So the activation energy is lowered by the catalyst. Light, there are some reactions that will take place, and they use light as a catalyst. In photography, where there is decomposition of silver, so the light in photography, the light affects the silver bromide and change it into the silver metal. So the silver metal, this silver metal that is formed will be deposited on the surface. So it is, in the photography, they use light to decompose the silver bromide into the silver that will coat the surface of the metal. So let us continue with our questions. So we look at, because we said we're supposed to answer some of these questions. Question number one is said, name a biological process that requires light to take place. A biological process that requires light to take place. I will be giving you some few seconds to answer the questions. This is photosynthesis. So this is number one. A, we have photosynthesis. B, enzymes act as catalysts and are found in mold, should be molds, and bacteria that spoil the food. Molds are these substances that grow on a bread. When the bread is getting expired, there are some substances that grow there. And explain using the knowledge of factors that affect the rate of reaction why food does not spoil as fast when it is refrigerated as it would when at room temperature. So putting the food in the fridge, the food takes much longer time to get destroyed than leaving it there in the open space. Why? So what happens, whatever you put in the fridge, that means that lower temperatures, so we come back to the effect of temperature. If the temperatures are very low, there are chemical reactions that take place that will destroy the food. Chemical reactions, so when the temperatures are low, that means the rate at which those chemical reactions that may lead to spoiling of food also reduces. And therefore, the food in the fridge takes longer time than at any other temperature outside the fridge. So we can say, in the fridge, the temperatures are low. The temperatures are low, and this lowers the rate of reactions that may lead the food to go bad. It is just the effect of temperature that is being applied in here, lowering the temperature. So that means the reactions that lead to the destruction, leading to the food going or being spoiled will go low. Maize flour catches fire and burns when sprinkled into a frame. Maize-gained grains take long to burn when dropped into the same frame. Explain. One other factor here that we have forgotten is the effect of surface area. The effect of surface area. So the surface area here, we are talking about when you have the maize flour, it is in powder form. So the surface area is increased. Surface area is very large. Maize grains have a smaller surface area. So that means the rate of the reaction will be increased as you increase the surface area. So here we are applying the effect of the surface area. So that's why the maize flour easily catches fire, because of the high surface area compared to the maize grains. So can say, see, maize flour has a large surface area compared to maize grains. And that's why it easily catches fire. Which two conditions may accelerate the process of rusting? So rusting is a process that takes longer, takes some days. So which other two processes do you think can accelerate the process of rusting? Well, so this here, the process of rusting can be accelerated by addition of, if you add sodium chloride, that is salts. Just do it at home and see where you are. It is just a simple experiment. Just take maybe a small iron nail, put it in water, put it in open space, and get another one where you have to add, instead of adding water, so add a solution of sodium chloride, and you see which one will take place faster. So this one, when you increase the temperature, increase the acidity of the solution. Acidity of the solution. That means adding some acids. That also can also accelerate the process of rusting. Burning of substances in pure oxygen is a very fast process. However, the process is slowed when they burn in air. Burning of substances in pure oxygen is a very fast process. However, the process is slowed when they burn in air. So what is the implication of that? In pure oxygen, there is accelerated burning. But in pure air, that means pure air contains some other substances. That makes another sense that pure substances, air contains other substances that may interfere with the burning process, And how does it interfere with the burning process? Because if the number, that means the oxygen in the air compared to the oxygen in the, which is pure, are different. So the factor of concentration again. So burning is accelerated because in pure oxygen, there is high concentration of oxygen. In pure air, the concentration of oxygen is lowered, and therefore burning is slowed down. When iron filings and iron nails are left exposed in air for some days, both will rust. Iron filings are powdered up, small particles, and then nails are bigger. So the effect of the surface area still comes in. So the iron nails will rust faster, now the iron filings will rust faster compared to the iron nails because of the increased surface area. So we have increased surface area. This was part D, and then we have A, which is state the conditions necessary for rusting. I think even primary 4-5 there can be able to state the conditions for rusting. So we have water. There must be presence of water, and there must be oxygen. This water and oxygen are the most necessary conditions for rusting. Which of the two will rust faster, iron nails or iron nail? I've talked about the effect. Iron filings rust faster. Why? Because of high surface area. So the small particles are exposed easily to the oxygen and water. Because they are exposed, every particle is exposed to air and water. And therefore, that's why the rusting will take place faster than expected. Number two, various experiments were carried out by students using magnesium ribbon of unequal length with excess dilute hydrochloric acid. The observations were recorded in the table below. These are the observations. Write a balanced chemical equation for the reaction. Magnesium ribbon with excess dilute sulfuric acid. Magnesium ribbon with excess sulfuric acid. I think you are writing it down. Magnesium ribbon, so that is magnesium metal. And you reacting it, magnesium plus hydrochloric acid. This will give magnesium chloride plus the hydrogen gas. So that is the reaction, balanced reaction between magnesium and hydrochloric acid. Draw a graph of evolution of hydrogen gas against the length of the ribbon. So I've just tried to draw the graph for you. On this graph, this is the graph of the magnesium, of the evolution of hydrogen gas against the length of magnesium ribbon. This is the graph. There are some things I want to talk about this graph. Make sure whenever you are drawing the graph, at least your graph covers 3/4. If this is the graph, paper, the 3/4, I mean the whole of this part. Maybe if I divide this paper into 4 equal parts, probably this will take the 3/4. I mean, maybe this is a quarter. That's just an approximate. And then you have to use the scale that is very clear. 3/4 of the graph, and then the scale must be clear. That is what we are looking at. So going back briefly, from the graph, determine the rate of evolution of hydrogen gas when the following lengths were 1.5. So that is 1.5. If the graph is moving like this, and then I go to 1.5 here, and then draw a line, then determine the volume of the gas that is produced here. That is 1.5, then I move and then determine the volume. Then if they say 4.5, so here I say 4.5 centimeters, the same. I go to 4.5, draw the line, then read the volume here. So it is just as simple as that. Then on the same axis, sketch a graph that would be obtained. So that is the graph. This is the sketch graph that has been obtained. And how has it been obtained? That would be obtained if powdered magnesium. So the powder was, the magnesium, it was ribbon, and then changed into from the ribbon to powder. So that means this must be at least take place faster and therefore slightly above this one here. So this was the original. This is for magnesium ribbon, but this is for magnesium powder. So you have to take, you have to consider the two. That means the surface area of these substances are also still considered. So it is very important to consider even when you are drawing the graphs. Probably, I'll just need to take you to some of the things that I want you to work on. Oh, sorry. So this is what I want you to look at as part of your homework. Before we wind up, I want you to look at this question. Homework. When aqueous sodium thiosulfate and dilute hydrochloric acid are mixed, a precipitate of insoluble sulfur is produced. This makes the mixture difficult to see through. This is the reaction. The time taken for the cross to disappear from the view is measured. And then when you measure, this is the information which includes the question. A student adds the following volumes of aqueous sodium thiosulfate, dilute hydrochloric acid, and distilled water, the conical flask. The time taken for the formation of precipitate of sulfur to make the cross disappear from the view is recorded. So this is the volume of sodium thiosulfate, the volume of hydrochloric acid, the volumes of water, time taken for the cross to disappear. State the order in which the reaction, in which the aqueous sodium sulfate, hydrochloric acid, distilled water should be added in the flask, and then you explain that. So the last one, this is part B. So you can also take note of that one. As we come to the end, we will still, in the next lesson, we'll have to also look at some other, in the other 30 minutes, we'll also have to look at some other questions, and we should be having as many questions as possible, and that will also make us more understood the lesson more. I thank you so much for listening and watching. I hope we'll be together in the next lesson. Bye-bye.